Okay, in this video I'm going to do some exercises involving cosets. You can see the word coset right here. Okay. Coset is a type of set within a group that's defined in terms of a subgroup. So I'm going to do two of these exercises, exercise 5B and exercise 5H down at the bottom. And notice that these two exercises are on page 120 of your text. These are the exercises after the cosets chapter. All right, so let me go ahead and do number 3. Part B, that is. Okay, so part B is this one. I'm going to do the cosets associated with the cyclic subgroup generated by 3 within the group U8. All right, so let's recall what these things are. We remember that U8, that's the natural numbers that are relatively prime to 8 and are less than 8. And so here we have 1. 2 is not relatively prime, so we have 3. 4 is not relatively prime, so we have 5. 6 is not relatively prime, so we have 7. Okay, so that's the set U8, and the group operation. The group operation is multiplication, mod 9. Mod 8, sorry, mod 8. Okay, so that's the group that we're working in. Now, in order to define cosets, we need a subgroup. This subgroup that we're looking at is the cyclic group generated by 3. So to find that set, we can start with 3. Remember how we generate this set is we take 3 times 3 and then take that mod 8. So that's going to take us to 3 times 3 is 9. Mod 8 is 1. Okay. Then if I take 1 times 3, I'm back at 3. And if I keep multiplying by 3, I will always remain within this set. Okay, so this is the cyclic subgroup. Okay. All right. Now, notice that if I take all of the elements in this cyclic subgroup and multiply by another group element, I'll get another set. For instance, let me take the element 5. If I take the element 5 and I multiply it by every element in this cyclic subgroup, I'll write that this way. It's 5 times angle brackets 3. Okay. If I do that, then I'll get 5 times 3. And again, this is multiplication mod 8. And I'll get 5 times 1. And that will give me the set 15. Now 15 mod 8 is what? Well, subtract 8, that gives me 7. 15 mod 8 is 7. And then 5 times 1, of course, is 5. Okay, so if I take the 5 multiplied by the cyclic subgroup, I get this other set. And this is this set is actually called a coset of 3 that contains 5. Okay. Now I could do the same thing with the element 7. If I took 7 times this cyclic subgroup, I would get, well, you get 7 times 1 times 3 and 7 times 1. Now if I take 7 times 3, that's 21. If I take 21 mod 8, well, let's see. If I subtract 16, that's going to give me 5. So in fact, that's equal to 5 and 7. Okay. All right, so in fact, this is the coset of 3 that contains 7. Notice that if I'd multiplied the cyclic subgroup generated by 3 by 5, I get this set. And I also get the same result if I multiply by 7. Okay, so I actually end up with the same set. Okay, so this is the coset containing containing 7. Now I could do the same thing with 3. If I took 3 times angle brackets 3, that would give me, well, you get 3 times 3 and 3 times 1. And that's going to give me 1, 3. And that's the same thing, of course, as 3. Okay. So the situation here is as follows. My entire group U8 contains the points 1, 3, 5, and 7. Now notice that angle brackets 3 itself is the upper half of this set. So this part here is angle brackets 3. And the lower part here I could write as 5 angle brackets 3. Okay. And this also equal to 7 angle brackets 3. Okay, and this angle brackets 3 is also equal to 3 angle brackets 3. Now each time I multiply this cyclic subgroup by an element in the group, I get a coset. I either get this coset, which is the original subgroup, or this second coset, which is disjoint from the original subgroup. Okay, so just to emphasize, this 5 angle brackets 3 and 7 angle brackets 3 are 2 different ways of specifying the same coset. And notice the important property here that cosets form a partition of the entire group. Okay, that's one important property. Another important property that you can see from the way that cosets are defined, notice that when I define this coset 3 times angle brackets 3, I'm multiplying each element of angle brackets 3 by 3. Right? So if I start out with 2 elements in angle brackets 3, I'll end up with 2 elements in 3 times angle brackets 3. The point here is that every coset will have the same number of elements as the original subgroup. So all cosets have the same number of elements. And that's equal to the number of elements in the subgroup. Okay, because the subgroup itself is in fact a coset. Okay. All right, so I've given you some extra information here just to summarize the answer here. It says list the left and right cosets of these subgroups. All right. What I've done here is the left subgroups because I've multiplied what I found is the left cosets. Sorry, I think I said that wrong. I found the left cosets because I multiplied the original subgroup on the left by group elements. Okay. So to summarize, I have the left cosets of 3 in U8 are 1, 3 and 5, 7. Okay, so the cosets are sets themselves. So if I'm going to list the sets, I should list them as a set of sets. This is the set of cosets of angle brackets 3 in U8. Okay, what about the right cosets? All right, now in this case, you can see that the multiplication is commutative. So whether I take 5 times angle brackets 3, or I take angle brackets 3 times 5, if I multiply all the elements of angle brackets 3 on the right instead of on the left, I'm going to get the same result. Okay. And I also have angle brackets 3 times 7. 7 times angle brackets 3 is equal to angle brackets 3 times 7. Okay. So in this case, the left cosets are equal to the right cosets. And you can see that this was always going to be true since the group is abelian. Okay. Okay, so whenever you have an abelian group, it's quite clear that the left cosets and the right cosets will be equal to 0, will be equal to each other. So the right cosets are the same thing. Okay. So those are my two answers. This is for the left cosets here. And these are for the right cosets here. Okay, so that was a fairly easy problem. I also gave myself a harder problem here. This problem here for H, which are the cosets of this subgroup in S4. Remember, S4 is the permutations of 4 symbols. Here, our 4 symbols are going to be 1, 2, 3, 4. So let's go ahead and get started with that. So I'm going to select this text here to save it. And we'll copy. And I'm also going to take this and let's just take this and get rid of all this. And let's see if this will paste. Okay, here we go. So let's go ahead and try this problem here. Okay, so what about S4? S4 is actually a fairly large group. S4 is equal to the permutations of 1, 2, 3, 4. If you think about it, this has how many elements does this have? Well, it has 4 factorial elements because 1 can go to anything, so that's 4 possibilities. Then once the image of 1 is fixed, then 2 has 3 remaining possibilities. Once 1 and 2 are fixed, then 3 has 2 remaining possibilities, etc. So that has 4 factorial elements equals to 24. And here I have the order of H, of course, is equal to 3. Okay. Now, to find cosets of H in S4, what I'm going to want to do is a similar process to what I did before. I'm going to take H, and I'm going to multiply. Well, let's do the left cosets first. To do the left cosets, I'm going to have to multiply on the left by group elements. Okay, so let's take H and let's multiply H by a group element on the left. All right, so here we have 3 group elements. It turns out if I multiply H by one of these group elements within H, I'm just going to get H back again. That results from the property of closure of subgroups. So let me try a different element of S4 and see what set I get. So let's see, here I have all, these are all 3 cycles. This is the identity. So let's try something like this. Let's try 1, 2. Okay, if I do that, then I'm going to get, then when I multiply 1, 2 times 1, well, let's do that out like this. I'm going to have 1, 2 times 1. Then I'll have 1, 2 times 1, 2, 3. And then I'll have 1, 2 times 1, 3, 2. Okay. And that's going to give me, well, the first one is just going to give me 1, 2 again. Second one, I have to figure this out. 1 goes to 2, 2 goes to 1. That's actually fixed. Okay. 2 goes to 3. So let's take this. So this is going to give me 2 goes to 3. And if you see 3 goes to 1, 1 goes to 2. So the second one is 2, 3. Okay. How about this one here? I have 1 goes to 3. Let's see what 3 goes to. 3 goes to 2, 2 goes to 1, 3 goes to 1. And you can check that 2 goes to 2. I'm sorry, 2 goes to 2. 2 goes to 1, 1 goes to 2. Okay, so this is the result I get when I take the permutation 1, 2 times the group H. Okay, notice that this is a set which is disjoint from H and it has the same number of elements. Now notice also, often I find that students make this mistake. This is not a subgroup. Cosets in general are not subgroups. I'll say that again. In general, cosets are not subgroups. There's only one coset in a set of cosets that's the subgroup, and that's the original subgroup that is used to generate the cosets. So this coset is not a subgroup. It does not contain the identity. And it can't contain the identity because cosets are supposed to be disjoint. All right, so I found one more coset. This coset has 3 elements. Now, actually, at this point, we can tell how many cosets we're going to have. Why is that? Because we know we have 24 elements total, and we can see that each coset is going to have 3 elements in it. Okay, so we're going to actually be dividing the entire 24 element set up into 3 element cosets. So how many cosets is that? Well, get out your calculator or use the computer and take a few hours to do that, and you'll come up with a number 8. So we expect to have 8 cosets. And we have 2 already. So let's keep going. Now, how do we get another coset? Well, we want to multiply H by another element. And we've taken care of some of these elements. We don't want to multiply H by any of the elements we've found so far, because then we'll get the same cosets. But we want to multiply H by something else. Well, let's see. S4 also includes permutations of 4. So let's try a permutation with 4 in it. Let's take 1 4 times H. Okay. If we do that, let's see if we can, we'll do this again. That's going to be 1 4 times 1. And then we'll have 1 4 times 1 2 3. And then we'll have 1 4 times 2 3 1. Okay, so you need to get very, very good at multiplying permutations. Okay, so the first one is I'm going to have 1 4. Second one is going to be 1 goes to 2. That's all. Then 2 goes to 3. And then let's see, 3 goes to 1, 1 goes to 4, 3 goes to 4. So we got 1 2 3 4 there. Okay. Then let's try this one. This one has 1 goes to 4. Then we have 4 goes to 1. And then, did I do that right? I'm sorry, that's not correct. It's not correct that 1 goes to 4. Let's do that again. Actually, 1 goes to 2. And 2 goes to 3. 3 goes to 1, 3 goes to... All right, I think I made a mistake here. Let's do this more carefully. Oh, that's because I wrote this one wrong. This should be 1 3 2. Sorry. That's my mistake. This should be 1 3 2. Okay, now I think we're back on track. So let me erase this. Okay. And we'll do it correctly this time. Okay. So here we have 1 goes to 3. 3 goes to 2. 2 goes to 1, 1 goes to 4, so this 2 goes to 4. 4 goes to 1, there we go, finally. Okay, so we have another coset here. Let's try also 2, 4, because that's not included in this group, and see what happens there. Okay, so that's going to be 2, 4 times 1. And then we'll have 2, 4 times 1, 2, 3. And then we'll have 2, 4 times 1, 3, 2. And that will give us 2, 4. Now let's see the next one. 1 goes to 2, 2 goes to 4, so that's giving me 1, 4. 4 goes to 2. 2 goes to 3. And 3 goes to 1. Okay, so we have 1, 4, 2, 3. And I think that we can expect the other one is going to be 1. Let's see what the other one is. Okay, 1 goes to 3. 3 goes to 4. 4 goes to 2. Okay, how many cosets do we have so far? 1, 2, 3, 4. Okay, all right. Let's try 3, 4, and see what we get there. Okay, I'm going to start out with 3, 4. Okay, let's do this next one. Here I have 1, 2, 3. 1 goes to 2. Let's see what 2 goes to. 2 goes to 4. And then 4 goes to 3. Okay, and then this last one, 1 goes to 4. 4 goes to 3. And 3 goes to 2. Okay. Okay, so I have 1, 2, 3, 4, 5 cosets. That's not everything. Seems like I've run out of stuff to do, but I haven't. Notice the cycle structure of the permutations I have so far. I have 2 cycles. I have 4 cycles. And I also had I also have this one, the original H, I have 3 cycles here. Okay, but I don't have any 3 cycles that contain 4. All right. So let's try a 3 cycle that contains 4. For instance, I could do 1, 2, 4. In that case, I'm going to get, now notice that I'm always choosing permutations to multiply by H that I haven't included yet. The permutations I've included so far are these 3, these 3, these 3, these 3, these 3. Okay, so I want to multiply by a new permutation. So that's going to be 1, 2, 4 times 1. Then 1, 2, 4 times 1, 2, 3. And then I'll have 1, 2, 4 times 1, 3, 2. Okay, so here I have 1, 2, 4. This one I have 1 goes to 2, 2 goes to 4, so I have 1 goes to 4. And 4 goes to 1, so this closes. 2 goes to 3. 3 goes to 2, so I get this one. Okay. Next one, a little bit surprising here, but that's what happens. I multiply a 3 cycle by this other 3 cycle, I get 2 2 cycles. Here I get 1 goes to 3. And you can work out that this gives you 1, 3, 2, 4.